Right now, the physics keeping your feet glued to the floor and the physics operating the smartphone in your hand, they actively hate each other.
Oh, completely. It's like they're speaking two entirely different languages.
Right. They went on two completely different rule books, and if you try to combine them, the math that holds our universe together literally blows up.
Yeah, it's arguably the ultimate scientific open secret. The entire framework of our modern physical understanding is supported by two distinct pillars, and those two pillars, when forced into the same room, completely repel each other.
Welcome to today's deep dive. We are pulling from a really fascinating essay today by a theoretical physicist exploring this decades-long search for a theory of everything.
And our mission today is to break down this grand scientific mystery for you. And we're assuming zero prior science background here, so don't worry.
Exactly. We want to take our time, keep it unhurried, and really just understand the biggest unsolved puzzle in the universe. Because, well, here's where it gets really interesting. Some of the absolute greatest scientific minds of the last century, the brightest geniuses we have ever produced, have spent their entire careers trying to solve this puzzle, and they have just hit a brick wall.
Yeah, it's still genuinely, honestly unsolved.
Which is wild.
Which is exactly what makes it so compelling to explore. We aren't talking about a minor rounding error in a lab somewhere. We are talking about a fundamental clash in how the universe operates at its core.
Okay, so if the universe is running on two conflicting rule books, where do we even begin? I assume we have to look at the individual rule books first just to understand why the map of reality is broken.
Yeah, that's definitely the best place to start. Before we can see the crack in the foundation, we really need to understand the two pillars themselves.
Right.
So let's look at the first one. Albert Einstein's general theory of relativity. This is, to put it simply, our theory of the very large.
The big stuff.
Exactly. It's the framework that governs planets, stars, entire galaxies, the life cycle of black holes, and, well, the grand expansion of the universe itself.
So when you say it governs the very large, we are talking specifically about gravity, right?
Yes, mostly gravity.
But the source text makes a huge point that this isn't the gravity that, most of us picture in our heads.
Not at all. When most of us learn about gravity in grade school, it's taught as a pulling force, like an invisible magnetic tether that the Earth casts out to hold the moon in orbit.
Yeah, or like a rope pulling an apple down from a branch.
Right, but Einstein completely reimagined that. Gravity isn't a pulling force at all. It is the literal bending and warping of space and time itself by mass and energy.
See, I know we always hear that classic textbook trampoline analogy for this, where space is a stretched-out trampoline and a bowling ball in the middle sinks down, creating a curve.
Sure, the trampoline.
But honestly, that always felt a bit two-dimensional to me. Like, we don't live on a flat sheet.
That's a very fair critique of the trampoline analogy. It works for a basic visual, but to really grasp what Einstein was saying, you had to think in three dimensions.
Okay, how I do that?
So imagine you are suspended inside a giant room-sized block of clear grid-lined gelatin.
Okay, weird, but I'm with you.
That gelatin is space-time. If you place a heavy lead weight right in the center of that gelatin, it doesn't just pull the surface down. It pulls all the grid lines inside the block toward it from every single direction.
Oh, wow. Okay.
Yeah, the space itself is thicker, denser, and curved toward that massive object.
So if I flick a little marble into that block of gelatin, it's not being pulled by the lead weight like a magnet. It's just following the natural curve of the grid lines that have been warped by the weight.
Precisely. The Earth orbits the Sun simply because the Sun is so massive, it has warped the space-time gelatin around it, and the Earth is just rolling along that invisible three-dimensional curve.
That is wild to think about.
And this theory is an absolute masterpiece. When you promote general relativity at anything massive in the cosmos, it delivers predictions of just breathtaking accuracy.
And the source text emphasized how smooth this all is, right? Like, the math relies on space and time being a continuous, orderly, and beautifully predictable fabric.
That word continuous is vital here.
Yeah.
General relativity demands a universe that curves elegantly, with no sharp edges or jagged breaks. It's a flawless, flowing, geometric landscape.
Okay, so if general relativity perfectly explains the cosmos and the elegant geometry of space, why do we even need another rule book? Where does Einstein's map stop working?
Well, it stops working when you zoom in.
Like how far?
Really, really far in. Which brings us to the second pillar, quantum mechanics. If general relativity is our theory of the very large, Quantum mechanics is our theory of the very small.
Right, atoms and stuff.
Exactly. It governs the microscopic world of atoms, electrons, and the subatomic particles inside them.
And this is where things get weird.
Deeply strange. Down at the scale of the truly tiny, the rules of reality change in ways that, frankly, defy all human intuition. In our everyday world, things are certain. A baseball is exactly where it is. It has a specific speed and a specific location. But in the quantum realm, particles don't behave like solid little baseballs.
The text mentions they behave like waves. What does that actually mean for the listener who is just, sitting at their desk or driving their car right now?
Look at the solid dashboard of your car or the desk in front of you. It feels completely still.
Yeah.
It feels absolutely certain.
It's definitely solid.
But if you were to zoom in to the atomic level of that plastic or wood, you wouldn't find tiny, solid, perfectly still dots. You would find a chaotic storm.
A storm?
Yeah, quantum particles exist in combinations of multiple possibilities at once. It's a world that operates on probabilities rather than absolute certainties.
Wait, so you're saying a particle isn't definitively in one spot?
It has a high probability of being in one spot, but it could also spontaneously be found somewhere else. It's smeared out like a cloud of chance.
That is just so hard to wrap my head around.
There's a famous concept called the double slit experiment, where a single particle, when fired at a barrier with two slits, actually passes through both slits at the exact same time.
Both at once?
Yeah, interfering with itself like a wave of water would. It only chooses a solid location when we force it to interact with a detector.
Okay, that feels entirely like science fiction. If the tiny building blocks of everything are just jittery, unpredictable probability clouds, how does anything solid exist? Like, how does my desk hold up my computer?
Because when you add up trillions and trillions of these probabilistic particles, the weirdness kind of averages out, and you get the solid, predictable world we live in.
Oh, I see.
It is totally counterintuitive to the human brain, which, evolved to deal with medium-sized objects like rocks and trees. But quantum mechanics is stupendously successful.
So it actually works.
Even if it sounds like magic, this theory underpins all of modern chemistry and electronics.
Wait, the smartphone in my pocket right now relies on this.
Absolutely.
Yeah.
The microscopic transistors inside your phone's microchips only work because engineers know exactly how to manipulate the probabilistic wave-like nature of electrons.
No way.
If quantum mechanics were wrong, your phone would be a completely useless brick of metal and glass. And what's fascinating here is that both of these theories, general relativity for the massive and quantum mechanics for the microscopic, are among the most successful ideas humans have ever produced.
Yeah.
They have been verified to an accuracy that just beggars belief.
Okay, let's unpack this. Well, because here's where the plot thickens.
Right.
We have this perfect, unbroken rule book for the big stuff with its smooth, elegant curves.
Right.
And we have a perfect, unbroken rule book for the tiny stuff with its jittery, fluctuating probability clouds. Why can't we just staple the two rule books together and call it a day?
I wish we could.
Like, why is there a contradiction at all?
Because the rule books don't just describe different things. They describe the actual nature of reality in fundamentally incompatible ways. And you see the mathematical explosion when you try to force them to talk to each other.
The source calls this the Great Clash. Walk me through the actual mechanism of this clash. Like, why does the math literally blow up?
So let's go back to how they view the fabric of reality. General relativity, our gravity theory, demands that space-time is smooth and continuous.
The gelatin.
Exactly. To calculate gravity, the equations need exact coordinates. They need to know precisely where point A is and precisely where point B is to measure the elegant curve between them.
Okay, that makes perfect sense. Gravity needs a reliable map with exact distances.
But what do we say quantum mechanics says about exact points?
That they don't exist. That they are jittery clouds of probability.
There you go. Quantum mechanics says that at the smallest possible scales, reality isn't smooth at all. It is restless. It is seething with random, violent fluctuations.
Wow.
So if you take the equations for gravity, which demand an exact distance between point A and point B, and you plug in the quantum reality, where point A and point B are constantly boiling, shifting, and jumping around, the equation just panics.
Because it's trying to measure a definitive curve across like a boiling pot of water.
Worse than that, actually. In mathematics, when you try to calculate the force of gravity at a quantum distance, a distance that is essentially fluctuating down to zero, you end up trying to divide by zero in the equations.
No.
And as anyone who remembers middle school math knows, when you divide by zero, the result is infinity.
The math literally spits out untamable infinities. It just completely stops making sense.
The two theories simply refuse to agree. The source text uses a really fantastic analogy for this. It says it's like having two flawless maps of the exact same country, but they're drawn to completely incompatible rules.
And you have absolutely no way to lay one map over the other.
Exactly.
Which, I mean, that raises an existential question. If the maps contradict each other, does this mean reality itself is broken?
Well, we can confidently say reality is not broken.
Thank goodness.
The universe exists, right? It functions perfectly well. The stars shine, the planets orbit, and the atoms hold together. Therefore, it has to be human mathematics that is failing to capture the whole picture.
We're just missing something.
Yeah, we have discovered two deeply profound truths about the universe, but we are missing the translation key that shows how they are actually the exact same truth.
So what does this all mean for the listener? I have to be honest, I am interacting with human-sized things all day.
Sure.
I'm not a jittery atom, and I'm not a swirling galaxy. If I have one map for the big stuff and one map for the small stuff, does this clash actually matter in the real world? Or is this just an abstract headache for theoretical physicists?
For the vast majority of physics, and certainly for everyday human life, no, you won't notice it. You use the big theory for big things and the small theory for small things.
And you just never have to cross the streams.
Exactly. You just keep the rule books on separate shelves.
Oh.
But the universe is not just full of ordinary things. It has extreme places.
Okay.
Places where the streams absolutely must cross. To find where the math breaks in reality, you need an environment that is extraordinarily massive, meaning it has immense gravity and extraordinarily tiny at the exact same time.
Wait, let me think about this. Nothing in my daily life is super heavy and microscopic simultaneously.
No.
The only place I can think of where something massive gets crushed down that incredibly small is a black hole.
That is the perfect example.
Yeah.
We know black holes exist. They are formed when giant stars collapse in on themselves.
Right.
And at the very center of a black hole, at the singularity, you have an unimaginably huge amount of matter. The entire solar system's worth of mass crushed down into a microscopic, vanishingly small point.
So because it is incredibly massive, general relativity insists it has to be involved.
Yeah.
But because it is microscopically tiny, quantum mechanics kicks the door down and says, no, I have to be involved.
Yes. You desperately need both theories to understand what is happening at the center of a black hole. But when you try to use them together, they fail you.
That's crazy.
Take time, for example. What happens to time at the center of a black hole? General relativity says immense gravity slows time down, bending it smoothly. But quantum mechanics says at that tiny scale, time itself should be jittery and fluctuating.
So does time stop? Does it fragment into pieces? Does it boil?
We literally do not know. The equations give us infinity. They give us pure nonsense.
Wow.
And another perfect example of this clash is the very first instant of the Big Bang.
The birth of the universe.
Nearly 14 billion years ago. The entire cosmos, all the matter and energy that currently makes up hundreds of billions of galaxies, was compressed into something unimaginably dense and incredibly tiny.
So it's the exact same problem. Massive gravity, microscopic size.
Right. To understand these frontiers, scientists desperately need a missing puzzle piece. They need a single theory that unites gravity with the quantum world.
And what do they call that?
This sought-after solution is known as quantum gravity.
Quantum gravity. A single theory of everything. But since we don't have it, we are essentially blind.
Yes.
If we don't find this theory, are we permanently locked out of understanding our own cosmic origin story? Are we just never going to know how the universe was actually born?
Until we solve this contradiction, those extreme frontiers remain deeply shrouded in mystery. We can rewind the clock of the universe back billions of years with astonishing precision, but when we get to that final fraction of a second at the very beginning,
It breaks.
our greatest theories fail us precisely where we need them to shine.
That is equally terrifying and incredibly exciting. It means the book isn't finished, and the source text highlights that physicists haven't just thrown their hands up, right? They are actively trying to build bridges between these two worlds.
They absolutely haven't given up. Physicists have proposed some incredibly bold, wildly imaginative ideas to try and bridge this gap. And the most famous of these proposed solutions is something that has saturated popular culture: string theory.
String theory. Yes, it sounds like something out of a sci-fi movie. I hear the term all the time. But how does it actually attempt to fix the contradiction between smooth gravity and jittery quantum mechanics?
To understand string theory, we have to entirely rethink what a particle is. Traditionally, Physics has thought of the most basic building blocks of reality like electrons or quarks as tiny dots, little zero-dimensional points of solid matter.
Okay.
String theory makes a wonderfully imaginative suggestion. It says, what if we zoom in on those tiny points and find out they aren't solid dots at all? What if they are actually incredibly tiny, one-dimensional vibrating strings of pure energy?
Wait, back up. I need to push back on this because it's a stumbling block for a lot of people.
Sure. Go ahead.
If an electron or a quark is a physical piece of matter, how can it just be a vibration of energy? Like, what is actually vibrating if there's no physical dot?
It's a great question. And it requires letting go of our everyday idea of stuff. In string theory, the energy is the stuff. The string itself is the fundamental unit of reality. The source provides a fantastic analogy here to help visualize it. Think of a guitar string.
Okay, I can picture that.
If you pluck a guitar string one way, it vibrates at a specific frequency, and you hear an A note. If you change the tension and pluck it differently, it vibrates differently, and you hear a C note.
Right.
It's the exact same physical string, just vibrating in different patterns.
So just like plucking a guitar string differently gives you different musical notes, different vibrations of these microscopic strings give you all the different particles that make up you, me, and the stars.
Precisely. In string theory, the universe is like an unimaginably complex symphony. One type of vibration gives you an electron, a different vibration gives you a photon of light, and crucially, wonderfully, yet another vibration naturally produces the graviton.
The graviton, what's that?
The theoretical quantum particle that carries the force of gravity. String theory naturally weaves gravity into the quantum world without the math blowing up into infinities.
Wow, that sounds incredibly elegant. It replaces a universe of disjointed, conflicting particles with a universe of unified strings.
It is very elegant.
But the source text doesn't just stop at string theory. It mentions that this isn't the only horse in the race. There's another theory trying to solve this called loop quantum gravity.
Yes, and we really need to give loop quantum gravity its due, because scientists are attacking this from multiple, vastly different angles.
How is it different from strings?
Well, if string theory tries to fix the problem by changing our definition of matter turning particles into strings loop, quantum gravity tries to fix the problem by changing our definition of space.
Changing space itself, how do you even do that?
Well, remember how general relativity relies on space being a smooth, continuous sheet of gelatin?
Yeah.
Loop quantum gravity says, what if Einstein was wrong about that specific detail? What if space isn't continuous? What if space is quantized?
Meaning space itself comes in tiny individual chunks.
Exactly. Think of a digital photograph on your computer screen. If you look at it from a distance, the image looks perfectly smooth and continuous, right? The colors blend seamlessly.
Right.
But if you zoom in far enough, you realize the image isn't smooth at all. It is made of thousands of tiny, discrete, individual square pixels.
Ah, okay. So loop quantum gravity is saying that if we zoom in far enough on the empty vacuum of space, it isn't a smooth sheet. It is made of tiny, individual, discrete loops or pixels of space woven together.
That's it. Space itself has a minimum possible size. And if space is made of discrete pixels, then things can't fluctuate down to zero distance. There is a hard limit to how small things can get.
Oh, which fixes the math.
Exactly.
Yeah.
By introducing a minimum size to the fabric of reality, the mathematical infinities that usually plague quantum gravity simply disappear. The math stops blowing up.
If we connect this to the bigger picture, we have these two brilliant theories. We have string theory playing a cosmic symphony of energy, and we have loop quantum gravity revealing the hidden pixels of space itself.
Both very compelling.
Both sound mathematically sound. Both seem to solve the contradiction. So why isn't one of them just taught as hard fact in textbooks? Why is it still a search for a theory of everything?
This raises an important question about the ultimate roadblock in modern physics. And it comes down to the fundamental, non-negotiable reality of the scientific method.
Which is?
An idea, no matter how intellectually elegant, no matter how beautifully the math works out on a chalkboard, only becomes established science when an experiment can physically check it.
You have to be able to prove it in the real world. You need evidence.
You have to test it. And here we hit a colossal obstacle. The scales at which theories like string theory or loop quantum gravity differ from ordinary, everyday physics are so extreme that we simply cannot reach them.
They're too small.
The strings in the space pixels are theorized to be so unimaginably small that testing for them would require energies that are truly mind-boggling.
How colossal are we talking? Like, could we build a bigger particle collider, like the Large Hadron Collider they have at CERN in Switzerland? Could we just build a bigger one to smash particles harder and find these strings?
The collider at CERN is a 17-mile ring and a total marvel of human engineering. But to probe the unimaginably tiny scales where string theory operates, the math suggests you wouldn't need a collider the size of a city.
Okay.
You would need a particle collider roughly the size of our entire galaxy.
The size of the galaxy.
Yeah, we simply do not possess the technology or the ability to harness the sheer cosmic energy required to run the experiments.
So to be incredibly clear here, these aren't answers yet.
Not definitively, no.
They're just really beautiful, mathematically coherent candidates, essentially sitting on a shelf waiting for human technology to catch up, like millions of years from now.
That is the harsh reality. They remain fascinating, serious, but fundamentally unproven proposals. The decisive experiments are, for now, completely beyond our reach.
I can imagine some people hearing this and feeling a bit let down. It almost sounds like a defeat. Like, oh, the scientists actually have no idea what they're doing.
But it shouldn't be framed as a defeat at all. The source text makes it very clear this isn't an embarrassment. It's a wonderful, honest illustration of how science actually works in real time.
Right.
Science isn't a dusty textbook of finished facts that physicists quietly guard in a tower. It is a living, breathing, messy process. The unification of quantum mechanics and gravity is a real, open frontier.
And the smartest people alive haven't cracked it, which means there is still room for a massive paradigm shift.
Precisely. It's entirely possible that string theory and loop quantum gravity are both slightly wrong, and the ultimate answer will come from a direction no one has even thought of yet.
Like a completely new idea.
It might require an intellectual leap as revolutionary as Einstein's was a century ago. A young student listening to this right now might be the one to figure it out in 30 years.
That's amazing to think about.
This frontier is exhilarating. It is a constant reminder that for all our technological mastery, nature still holds a magnificent puzzle at its very foundations.
Which brings us to the end of our deep dive today. If there is one thing to take away from the sources we've unpacked, it's that the theory of everything is not a trophy currently sitting on a shelf in a physics lab.
Definitely not.
It is a profound dream that human beings are actively reaching for. The dream of a single, unified description of reality, stretching all the way from the largest expanding galaxy down to the smallest subatomic particle, with absolutely no contradictions at the seams.
Exactly.
We have two of the greatest theories ever devised, general relativity and quantum mechanics, and we have the humbling fact that neither can be the final word.
Somewhere out there, beyond the reach of our current math and our current machines, lies a deeper, hidden truth that naturally contains them both.
And finding it would arguably be one of the crowning achievements in the history of human thought. But I want to leave you, the listener, with one final provocative thought to mull over, building on everything we've just discussed.
Oh, I like this.
We've talked extensively about how the universe operates on fundamentally different, incompatible rules, depending on how closely you zoom in, from the smooth, geometric gelatin of gravity down to the jittery, pixelated probabilities of the quantum world. But what does that say about the limits of our own human perception?
That is a profound philosophical question.
If zooming in changes the rules of reality completely, what happens if we could zoom out? If we ever manage to step back far beyond the scale of the cosmos, looking at the entire universe from the outside, might we find yet another set of rules waiting to contradict everything we think we know?
It's entirely possible.
When you look at that magnificent edifice of modern physics, remember that its foundations are still a glorious, beautifully flawed work in progress. Thank you so much for joining us on this deep dive. Keep questioning the everyday things, keep wondering about the impossible, and never stop looking at the universe around you.